Welcome to the Crazy Hat Chemist. So another video in solutions, and boy do I have a solution here for you today in chemistry. Bam! Today we're talking about a freezing point depression calculation. I want you to look at my picture right over there, and it's a giant truck in the Sierra Nevadas. And what it has in it is salt from a long time ago, and it is spreading salt on the highways. And why is it spreading salt on the highways? Well, it's because the highways, especially on bridges and tunnels, okay, they freeze over and then you get black ice, and that is extremely dangerous. So if you add salt with a Van Hoff factor of 2, that's sodium chloride, okay, then what will happen is you will depress the freezing point of the water. That means that water needs to get to a lower temperature before it freezes and forms black ice on the highways. So that's very important to have that spreading of that salt on the highways. I know it's not good for the environment, but now we also have trucks that scrape off the highway at the same time right there after this. Okay, so this works out very nicely, especially in the evenings when it's snowing and then you can't scrape off the highways soon enough. All right, so let's do a calculation here, and you should notice that almost all the calculations here are using the same set of information that I started off with in the original example. Okay, what is the freezing point of a solution containing 142 grams of ethylene glycol in 250 grams of water? Again, remembering that the solute is the least amount. The least amount is the 142 grams. The solvent is in the greatest amount. That's the 250 grams. So you know that the solute is the ethylene glycol. The solvent is the water. The freezing point constant for water. The solvent, that is found in a table to be KFP is equal to negative 1.86 degrees Celsius per molality. All right, so let's use this information and the equations of which we know to do our calculation here. The freezing point of the solution is equal to the normal freezing point of the solvent minus the change in temperature of the freezing point for the solution. So the normal freezing point for the solvent, that is water, is 0 degrees Celsius. This is going to be an exact number because I'm just pulling this out. I didn't bring it up and put it in the problem. Okay, the delta FP, that's delta TFP rather, is equal to the KFP times the I, the Van Hoff factor, times the molality. So I already know the constant. I'm going to plug that right in there. The I is for the solute. What is the solute? The ethylene glycol, and the glycol's formula here is C2H6O2. We already determined the Van Hoff factor for this of 1. So there is a 1 in place of the Van Hoff factor I. Now, I need to get the molality. Molality is moles of solute per kilogram of solvent. So I'm going to convert the moles of ethylene glycol, and that's down there at the bottom using the molar mass of ethylene glycol. I get 2.29 moles of ethylene glycol. That's going to go in the numerator. Then I'm going to take my 250 grams of water, divide by 1,000 to get kilograms of water, and then I plug into that molality equation. I'm going to simplify this here by doing a little division, and my quotient is 9.16 molal. So I'm going to plug in all these numbers, that is the constant, the Van Hoff factor, and the molality, and I'm going to multiply them all and get the change in temperature of the freezing point. So there it is. The change in temperature of the freezing point is the constant. That's negative 1.86 degrees Celsius per molal. The 1 for the Van Hoff factor, there are no units on that. It is an infinite number of significant figures because it is a counting number. And 9.16 molal for the molality of this solution. Okay, I'm going to get a number of 17.0 degrees Celsius. But wait, there's just a little bit that I want to put on here. Now, you could put a negative sign here, but I'm going to put this little note right here. And it says, either you can use the negative on this constant or perform the subtraction of the change in the freezing point. So it doesn't matter which one you want to do. So that is that 17 degrees Celsius that I have in the yellow right there. It could be a negative value, and then you're going to plug it into that top equation and then add it. Okay, remember, it's always a freezing point depression, so it's a decrease in the normal freezing point. That means the normal freezing point here for water is 0. That means you can't add 17 degrees to it and get 17 degrees Celsius, because that wouldn't make sense, because that would be a freezing point elevation, and that happens with boiling points, not freezing points. Freezing points are depressed, that is decrease. So I must get a value less than 0. So I'm going to plug this in here, so knowing that conceptually, you can either use the negative or subtracting. It's up to you. 0 degrees Celsius, that's an exact number, and then the minus 17.0 degrees Celsius, and I'm going to get negative 17.0 degrees Celsius for my final freezing point of this solution. So that means it must reach a temperature of negative 17 degrees Celsius before it starts freezing, with 142 grams of ethylene glycol in 250 grams of water. That is a super cool problem. Okay? I hope you enjoyed that video, and I got a crazy hat for you here. Go Oregon Ducks. Okay? Quack, quack. Give me a thumbs up if you like that video. Give me a thumbs up if you like the Oregon Ducks. Subscribe to my YouTube channel. Pass it on to all your friends. And I got one more video here for this entire unit. I can't wait for that one. All right. Bye now.